Hi, my name is Brian Slagowski, and this video is about my EE120 final design project. The project was about interfacing a 4x4 keypad, an EEPROM with a USB input-output board. So the overall block diagram is here, where we have a 4x4 keypad. Here we have the EEPROM, and here we have the 34-pin IDC connector, which interfaced with a USB I2 CIO board. So this was an 8-bit D-type latch, so that way we could send the address here and then send that to the EEPROM, because the data bus was all being shared here. And then we have 8 LEDs that we implemented onto the data bus, so that way we could have a visual output of the what was occurring on the data bus. And so with the information that was given to us, we had to go out and get all the pinouts and read all the data sheets of the individual pieces that were utilized in our hardware. So this is all the pinouts for each of the pieces, and then utilizing that information, the schematic here was created, or I created the schematic here. So in the schematic here, we have the 4x4 pin out. Here we have some pull-down resistors for half of the pins from this, because the 4x4 keypad, all it does is a short between two pins. And so here we have the 34-pin IDC with all of the actual labelings for all of the pins, and then this was the D-type octal latch, and here is the EEPROM, and then down here we have the LEDs here to monitor what's occurring on the data bus. And then from that point we can go over here to the actual design, or the actual breadboard implementation of it. Again, we have the 4x4 keypad, and coming in here, the pull-down resistors right here, the 34-pin IDC connector. This is the 8-bit octal latch with all the outputs coming in here to the addressing of the EEPROM, and then we have the data bus here, and then the EEPROM is connected to the data bus, and the LEDs down here are displaying the output of the data bus. And so, looking at the hardware, I'm going to explain the basics behind the software. So what we're doing is we're looking for a button pressed here, and then once a button on the keypad has been pressed, the software will detect it through the 34-pin IDC connector here, and then it will then decipher what button was actually pushed here, and then it will come here, relay the next appropriate address to the address latch, and then triggers the address latch to send the address to the EEPROM, and then we store the ASCII value of whatever button was pushed to the EEPROM. So if it was 1, then we would store a 30 in hex here. If it is an A, we stored 42 in hex to the EEPROM. And so that's the basic premise behind the software. And so then we can come over here and we can actually look at my flowchart. So here I have an input state for looking for button pushes on the actual keypad. Here we have the storage state, so once a button press has been detected, we go into the storage state. And then down here we have an output state, so once 2 buttons on the same row have been pushed on the keypad, we will then go into an output sequence displaying all of the buttons pushed in order, in the order that they were pushed. And so that's the basic flowchart for the program. And so here we have the actual code for the software of the program. I have an enumeration here for the state that we're actually in. This enumeration is for decoding or referencing the hex value of each button. And then here we're just declaring some variables, and here we're actually jumping into the program. This is the main switch for the state of the program. Here in the input state, we are checking or setting one pin on the keypad high, and then we're immediately reading the keypad to see if a button was pushed, because we can only check one row at a time. So we have to have one row high, and then we check corresponding columns for anything. If nothing is there, then we go to the next row and then check for the columns, and so on and so forth, until a button is detected. And once we've detected that, here is where we've actually detected a button push. If two buttons are actually pushed at the same time, we have to go into the output. So in real life, there's like a microsecond or a millisecond difference between one button and the two buttons being pushed. So we have to have this check in here to make sure that that's what the intent was to go to the output, and it wasn't the computer reading an input. This is about some extra stuff that wasn't required. I will go on later in. It's just something that I added into my program. And so here we are determining more about key being pressed. Here is an extra stuff that's not required. So in my program, if something wasn't actually pushed for a certain amount of time, then it would go into a standby state where one of the LEDs would light up, and then it would just sequence down the row where it just would be one LED and so on and so forth, and once it got to the end, it would then cycle back and forth, and it would just continually cycle down the row until a keypad was pressed, and then the keypad was pressed, and then whatever button was pressed, if it was a 1, then you would have a 1 and a 1, so these two here would be lit up for a 3, and then this would all just be blank for 0. So then that would be a 30. I mean, that would have been a 31. I'm sorry. So then that would have been a 3, and then these would be 0, and then that would be been on. So it's a 31 in hex for the 1. The 0 is 30 in hex. So that's what my program would do with that extra part, was a standby. The other extra part, I'll just cover it now, was on the output sequence. When the star was detected on the output, it would flash between AA and 5-5. So it would be kind of like bouncing back and forth, which I call it a twinkle effect, for a twinkle twinkle little star. And so that was what was going on in that point. And this right here is just the counter for determining if I was going to go into a wait state and just have the lights pulse through, and that's all this section here was doing. Here in the storage state, this is if the button 1 was actually pressed. When you do a port read, you would read a hex value of 88. So you have to then decipher the 88 and realize that was a 1. So then this is the value 31 in hex being put into the store data. And so once we decipher and do the changeover from the hex to actually what the ASCII value should be, here we have just a little update to let the user know what was actually stored, and we're actually storing the sequence here through to the EEPROM. Here in the output, once 2 buttons have been detected being pushed, we'll go to the output state, and so we're just reading out everything that was stored into the EEPROM, and we're also displaying it to the screen so the user can actually read it. And then this is just a default state, just in case something goes wrong, that you can go into the default state. And so that is the basics behind the actual code for my program. And so here we can see the actual output of the program to the user via the monitor. So here we are saying storing the data to a memory location. So we have the memory location 0, 1, 2, 3. And then here we have the values in ASCII that are actually being stored. And so here we have an address location. This is the output sequence here. And so that was the address location and the value that was stored, and it just goes through in sequence. And then so we also were required to hook up a logic analyzer to our program. So with the logic analyzer, we have here is the actual data bus that's being monitored, and so we were just required to look at the data bus during the output sequence. And so here we're starting the output sequence, and the address here is 0, and then we have some latch controls that you can't really tell are being combined in here, and then this is the value that was actually stored to the EEPROM. And then after a while, we have some more latch controls that you wouldn't see on the data bus. And then over here we have an address that's being put out to the data bus to go to the address latch. And then here we have latch controls that are occurring, but the data bus has a 0 on it. And then here we're going to the actual output from the EEPROM. And then again, address, latch controls, output, address, latch controls, and then here we have the output from the EEPROM, and then the 2A is the ASCII value for the star. And so here the computer registers what's on the data bus as 2A and displays that to the user via the screen, and also then on the data bus it pulses the AA55 to get the twinkle twinkle little star part, and that's what all of this over here is the twinkle twinkle little star thing, which was not required in the project. It was just this sequence here was all that was required, but I wanted to add this extra feature along with the standby state. And that concludes everything with my project. Thank you for watching my video.